So we go by the name SC now. It's called site engineering. So we had other teams like other than SRE teams also joining our work. So we went with the name SC. So first of all, good morning and welcome to the 40th large scale production engineering meetup, right? This forum is more about like meeting friends and all colleagues. So really happy to be here and seeing you all here, right? I know there is a line of really interesting talks, so I won't take a lot of time with my boring conversations, right? Just wanted to share some of the things which I felt about the large scale production engineering, the challenges and all. We'll share a couple of those things and we'll go over to that technical talk, which everyone is waiting eagerly to attend. So thinking about production engineering, the first thing comes into mind is like, the problem is so complex, right? And I don't think any organization across the globe has completely solved it. Even the larger organizations as well, right? Just reflecting at LinkedIn itself, we have a fairly internet scale operations running with around 800 million users. We serve at around close to 1 million queries per second on our edge servers. We have our infrastructure with 2 exabytes of data in Hadoop and around 17 trillion messages in Kafka, which we process every single day, right? It's a fairly large infrastructure. But even that infrastructure, we aren't close to where we can say that we have excelled in how to operate a large scale system. So recently we have launched something called SRE 3.0. So SRE 3.0 is a very simple concept, and it's a next, as you can understand, right? It's the next step of where SREs need to go, at least for LinkedIn, where we wanted to ensure that the operations are simple as well as self-serve for every engineer in the organization, right? Not limiting to SREs, but the developers as well, right? So tomorrow when the developers need to handle the applications which they develop, there is an ease at which they can manage their own applications which they build. So when you say that there is less toil in operating the application, so we have gone with taken that as the next step for SRE, right, where we will make operations simple and self-service for all the engineers in SRE. To reach there is a huge effort, right? So even smaller things like ensuring that there is an efficient tracing mechanisms, or just to make sure that the tools and the infrastructure we have is standardized. That's another issue with bigger organizations where we have built constant tech debt. We have built tools for the same purpose again and again, reinventing the wheel, not on purpose, but maybe due to other reasons, right? Also, we may have similar kind of infrastructure existing, right? So there is a huge gap which need to be filled in. Like for LinkedIn, this is the next step of journey. So the point which I was trying to drive here is that solving large-scale production infrastructure issues, or how we operate large-scale production infrastructures, is an unsolved problem. And if you think about the organizations may be in some place in that spectrum, right? So some people would have moved much further in the spectrum and have built efficient systems, processes to manage the infrastructure better. Some may be in somewhere in the middle, but only if you think about it, it's an unsolved problem. We have a lot of opportunity there. And every organization solves it in different ways, right? And learning from each and every one is the key, right? So Tribati was also mentioning this, saying that they have implemented it in their organization, but they are also trying to see like how other organization has implemented it. I think that is the key, right? Like learning from each other, sharing those experiences, right? So I want to take this moment to thank all the presenters for taking their time coming to this forum to share their knowledge, right? So thank you, Jeffrey, Asif, Tanya, Mohammed, Vivekanand, Devanshu, everyone for taking your time and coming to this forum to share your experiences and your knowledge. I also wanted to thank the folks who are running this forum, right? This is the 40th LSPE session, right? I remember the days when it started in Yahoo. We had a big crowd the first time when we started in Yahoo. Kudos to the folks who have been keeping it live and going strong, right? So the folks like Deepanshu, Badri, Prem, Anshu, Tripathi, Cook, Jessica, all these folks who have tirelessly and their perseverance, right, over the years, which has kept this forum up and running and going really, really strong. And they're thinking about increasing the frequency now, which is really, really great. So thank you for all those folks who have been keeping this forum up and running. I truly believe the next time when we meet, maybe we are going to meet in person. The pandemic is in the rear and we will be meeting in person. So looking forward for that day when we are all going to meet in person and going to have a blast. With that, I would leave the stage to the speakers. Thanks a lot. I hope you folks enjoy the day and there is a ton of learning. So with that, over to you, Devanshu. You can take over.
Okay, thanks a lot, Appu. This is nice. You clearly brought that production engineering is an unsolved domain, and unless we as community meet and learn from each other, probably this pollution will continue to be intriguing. So Prem and Batri, so you plan to run a video for 2 minutes. We have the time, so would you like to go for the video now?
Yes, it's just a one slide, Devanshu. You will just show up that slide. One moment. Let me do that. Are you guys able to see our screen?
Yes.
Yes.
Cool. So basically, first of all, like, thanks a lot, Devanshu. Like, it's been something super awesome. And as Appu mentioned, that 40th event and 10 years, it's something really amazing. With this, like, Appu gave a great introduction about LinkedIn and what's the future and where we are heading with respect to SE space as such. With this, we take a glad moment and we share that LinkedIn is hiring. And please feel free to reach out to Abhilash or any of us. Would be great to have you guys. Thanks a lot. With this, I hand it over to Badri so that he can introduce the speakers and he can take it forward. Hey, Badri. Looks like you are on mute, Badri.
Batri, you are muted. Please unmute and.
Just 1 second. I'm just getting it. Okay. Sorry for that. Now we're going to have the next talk about automations using Apache Airflow. Jeffrey Thomas from Data Platform SRE and Asif Jamadar from Database SRE from Twitter is going to talk about it. I welcome them and take over the hosting. Can you share the presentation?
Thank you, Badri. So these slides are visible, right?
Yep, we're good.
Okay. So hello everybody and welcome to our talk on using Airflow for.
Jeffrey, it's not in presenter mode. You have to share and present it, right?
I'm sorry, what exactly are you seeing right now?
No,
This is the right screen.
automation.
Yeah, this is the right screen.
Yeah, it's
No, unless you have multiple monitors, Jeffrey, you won't be able to use the presenter speaker notes thing.
okay. Okay, 1 second.
Or you need to do only this screen sharing, and the other side you need to, other window you need to have your notes.
Patri, can you make me host? Maybe I can share and let him talk about it.
Yeah. Who's meaning already Jeff and he has been made as a co-host.
Okay, or Asif, can you present then?
Yeah, Asif is also has been made as a co-host.
Okay. Asif, can you hear us? I think you're mute.
Oh, sorry. Yeah, can hear you.
Can you present so that Jeffrey can?
I'm doing that.
Thank you.
Actually, I'm using it for the first time, right? Zoom. So I need to allow the permissions to share the screen. Yeah, should be fine.
Tripathi, you have a presentation?
Yeah, I have. If you can make me the host, I can present. Or
Yeah, I can do that.
Okay,
you can do
I
that.
think already you are a co-host, Tripathi.
Should be fine. I'll just present that and let them talk through it. Oh, anyways, Asif is ready now.
Yeah.
That's good. Thanks,
Please,
Asif.
yeah. You see my screen, right?
Yeah, yeah.
I had to restart the meeting Zoom application itself to share my screen. Yeah, we should be fine now. I'll go to the first slide.
Thanks, Asif.
Jeffrey.
Thank you, Asif. So, hello everybody, and welcome to our talk on using Airflow for automation of SRE tasks. We will be focusing on how the data platform and the database SRE teams in Twitter have been using Apache Airflow to implement workflow that automate some of our operational heavy tasks. We will start with a brief overview of the scale at which data platform and database operates in Twitter. Then we will proceed to the challenges that made us explore workflow-based automation options. We'll touch on the basics of what Apache Airflow is, and then explain, taking up specific use cases, the implementations we did for data platform and database SRE teams. Finally, we'll open up the session for questions you may have. On to the introductions. My name is Jeffrey Thomas Jackson. My pronouns are he, him. I have been a part of the data platform SRE team at Twitter for the past 2 years. The data platform SRE team works on ways to reliably store and make available data especially big data, to teams of developers, data scientists, and business runners in Twitter.
Hey, I myself Asif, and my pronouns are he and him. I'm a senior database SRE working here close to 3 years, and it's been an amazing journey working with the team and helping the users have a good experience using the database services.
Okay, so let's start with a brief look at the scale of the data platform SRE team. One of the major services managed by the data platform SRE team is Hadoop and the infrastructure it runs on. Hadoop is a framework that allows for the distributed storage and processing of large data sets across clusters of computers. We have on-prem as well as cloud-based Hadoop clusters that are used for scheduled as well as ad hoc data processing jobs. Since the tasks we will be discussing in this talk are related to on-premise clusters, let me give you a brief overview of the scale at which we operate Hadoop on-premise in Twitter. We have multiple clusters running in multiple data centers, utilizing approximately 600K compute cores with a peak cluster size of around 12,500 nodes. The total logical storage capacity comes to around 500 petabytes, which consists of data that is generated from around 1.5 tera messages per day from the ecosystem of Twitter services. Next slide.
Yeah, so about databases. So we have like almost more than 100 plus MySQL clusters spread across multiple data centers. And on this 100 cluster, we have more than 3,600 databases, which are in dedicated cluster and multi-tenant cluster or shared cluster, you can say. And each database have more than one table. So those numbers are like 40K plus.
Now coming to the challenges that we were facing and the discussions around the reason for exploring Airflow and how we implemented Airflow. So one of the main operational challenges we faced when supporting such large clusters is the need for time-bound handling of maintenance as well as operational tasks. This becomes a major priority when we have tasks related to ensuring the cluster health is good, security compliance is adhered to, as well as streaming operational efficiency. These are all multi-step tasks that not always follow a sequential execution pattern. Also, when we are operating at such large scales, the engineer time investment required would be significant and not easy to incorporate in planning on a quarterly or even monthly basis. There is also the need to ensure that error-free execution of these tasks happen independent of the frequency and number of times they are executed. Next slide. So it was in this context that we started looking for a workflow-based platform that would allow us to clearly define task execution flows and dependencies. We looked at a couple of solutions and finally decided on Apache Airflow. It was an open source solution with inherent support for Python that would allow us to reuse our existing tooling code. An added advantage was that we had an internal team focused on taking third-party ETL solutions and adapting them as PaaS or SaaS frameworks to work well in the Twitter DevOps ecosystem. One of the solutions they support is Apache Airflow, which would make it easy for us to run up-to-date versions of the software with security patches and tested compatibility with Twitter's engineering tools and systems. So deploying, running, as well as maintaining the Apache Airflow clusters would be easy for us, and we could focus on designing our workflows in a better way. Next slide. A few words about Apache Airflow. Airflow was developed by Airbnb initially, but now it is under the Apache Software Foundation. Apache Airflow is an open source tool to programmatically author, schedule, and monitor workflows. Airflow is distributed, scalable, and flexible, making it well suited to handle the orchestration of workflows or pipelines. Airflow's rich user interface makes it easy to visualize pipelines running in production, monitor progress, and troubleshoot issues when needed. It also has support for connecting with multiple data sources and easy integration options with email, Slack, etc. for notifications. Airflow pipelines are defined as code using Python, allowing for dynamic pipeline generation and instantiation. Next slide. A directed acyclic graph or DAG is used to represent a workflow in Airflow. Dependency is very easy to express in Airflow because it uses this data structure. In the context of Apache Airflow, a DAG is a description of a collection of tasks in a way that shows each task's relationships and dependencies to say how they should run. You can have as many DAGs as you want, and the DAG itself doesn't care about what is happening inside the tasks. It is merely concerned with how to execute them, the order to run them in, how many times to retry them, if they have timeouts, and so on. To define tasks, we use operators that can be viewed as templates for predefined tasks. Airflow comes with several core operators and also makes it easy to define custom operators in Python. Next slide. So coming to our implementation. Our implementation considerations revolved around aspects like being able to monitor cluster state during task execution, being able to utilize existing automation and tooling code libraries, designing task relationships in a way to easily use the Airflow UI to view workflow progress, being able to send notifications and alerts using existing communication tools like Slack, Jira, and email. With the help of our internal team, we were able to quickly bootstrap the Airflow cluster in a distributed and scalable container-based infrastructure. Next slide. So let's look at the DP SRE or the data platform SRE use case we used to implement this. We implemented using Apache Airflow. The use case we are presenting here is the implementation for Hadoop minor version upgrade. The existing method used for Hadoop minor version upgrade had around 7 steps. These steps were being run using a partially automated approach in that we had tools that would automatically execute a certain series of commands that would constitute a certain part of the upgrade process on one or more components in the cluster. But manual intervention was necessary to trigger the tools at the appropriate step and monitor the progress of these executions. Some of the pain points we experienced were non-centralized invocation. So only the person who started it could properly view progress and status. Engineer attention for extended periods was necessary to act on failures or trigger the next set of automations. We have SRE teams working in 3 time zones and the tasks would be long running. But handover of execution to the next time zone mid-step wasn't possible because of the non-centralized execution model. The semi-automated nature also brought in the risk of human error as well. Next slide. So now let us see how the DAGs for the upgrade automation were designed. A Hadoop cluster consists of multiple node types running different types of services. You have name node and resource manager nodes that can be considered as managed nodes because they run services related to managing HDFS for storage and yarn for compute. Then you have worker nodes on which files are stored and jobs are run. These nodes have the node manager and data node services running to implement these capabilities. Additionally, we have a balancer node as well because we have HDFS federation implemented in our clusters. The upgrade process consists of identifying servers belonging to each node type and then running upgrade steps on the servers. The upgrade steps execution has to run on the servers in a fixed node type sequence, starting with the worker nodes, passing on to the name nodes, the resource manager, and finally the balancer node. Also, since the worker nodes consist of the bulk of servers belonging to a cluster, they are organized into failure domains called upgrade domains. This makes it easy to group worker nodes into batches for running of upgrade steps so that service restarts will not affect block availability. The DAGs for automating the upgrade process were organized into lower level, mid-level, and high-level DAGs. The high-level DAG has the node type sequence based on which the overall cluster upgrade would progress. Each step in the high-level DAG would trigger a mid-level DAG using the trigger DAG run airflow operator. The mid-level DAGs would determine an order to sequence the servers for upgrade under each node type. For workers, this would be upgrade domain batches, and for other node types, it would be individual servers. Each mid-level DAG would trigger a low-level DAG using the trigger DAG run operator. A low-level DAG contains the per server upgrade steps to be run on each server. The tasks in these DAGs were implemented using Airflow's Python operator, as well as a custom operator developed for our in-house remote command execution tool. So all this is illustrated in this slide. So initially we used variables to identify cluster information so that you would get the information about all the servers in the cluster and the different node types. And from that, the information would be passed to the first node type, which is the worker upgrade DAG. And that from this DAG, the next mid-level DAGs would be triggered actually, because you have multiple upgrade domains, and so you have multiple batches of nodes on which upgrade has to happen. So from there, first the upgrade the DAG for the upgrade of hosts in the upgrade domain 1 would be triggered, and then that in turn would trigger the DAGs for executing commands on each individual worker. Once a full batch of upgrade workers in an upgrade domain was complete, it would trigger the next upgrade domain DAG, and that in turn would trigger the next batch of workers. So after all the upgrade domain DAGs for the workers were triggered, the name node upgrade DAG would be triggered, and this would then in turn trigger a specific upgrade steps in a specific name node. So since we have HDFS federation, we don't have just one name node. We have up to 6 name nodes in a particular cluster based on the namespace federation, as well as the high availability implementation. So once all the name nodes would be upgraded, that's in the middle part, that's shown in the middle part of this flow diagram. Once all that the name nodes upgrade would complete, the execution would progress to the resource manager upgrade, and from there it would trigger the specific steps to be run on a resource manager. In the case of resource manager, it's just one node. Once the resource manager upgrade is complete, the balancer upgrade would happen. The balancer node is mainly to ensure that when HDFS federation is implemented, the distribution of blocks are done properly. So the balancer node steps are simpler, and once that is triggered, we would finally get a notification that the whole cluster upgrade is done. So at the top left, you can see a daemon node that is part of all our clusters, but it is not actually running any Hadoop services. That is like a maintenance node or a housekeeping node that we use to run certain cron jobs and all those things. So as the node type upgrades happen, it is easy to do the daemon node upgrade in parallel. It just requires some steps of updating some client libraries. Next slide. So here you can see examples or visualizations of the DAGs we wrote in each level and how they look like in the Airflow UI. So on the right, you can see low-level DAG, a representation of a low-level DAG. This consists of all the steps that are run inside a worker node. Specifically, once the upgrade, you initiate the upgrade in the worker node, there would be a change version step, then a restart of the services, and finally the end upgrade would determine whether the previous steps were run properly or not. And from there, the execution would, once that execution was complete and all the upgrades in a upgrade domain is complete, it would go back to the next upgrade domain node you see in the mid-level DAG that is in the middle of this slide. So it's not always fixed the number of upgrade domains you have in a particular cluster. It depends on cluster size and all those things. So in this case, this is a representation of a cluster that had 40 upgrade domains. So in turn, each upgrade domain DAG would trigger the low-level DAG shown on the right side. And on the left side, you can see the high-level DAG. This encapsulates basically, in the broader sense, all the upgrade steps that have to happen based on node types. So you have the workers, the name nodes, resource manager, and the balancer. And in turn, each node type execution would happen. Next slide. So a point I would like to mention about the organization of DAGs in this way is that it allowed us the ability to run individual node type upgrade DAGs separately if required, instead of always triggering a full upgrade of all the nodes. If certain, especially in the case of failures, if a certain node type needed to be rerun or run separately, we could do that. Some benefits that we gained from using this implementation are mainly a gain of around 60% SRE hours spent on upgrades. And there was a reduction of 30% in the cluster upgrade turnaround time. It also made it easier to validate the upgrade across all cluster components. And we could also run simultaneous upgrades of different clusters with involvement from only a single SRE. Another important factor was the requirement of not needing to have passing of handover nodes. We could ensure that the same standardized process would be followed regardless of who initiated the upgrade. And there was no need for constant watching of the upgrade progress, so that SREs could focus on other tasks while the upgrade of a cluster was going on. The rollback also was easy to perform. Next slide. Yeah, so that brings us to the end of the data platform SRE use case. We move on to the database SRE use case.
Thanks, Jeffrey. So let me share my experience using Airflow for our database SRE use case. So as I said that we have a very big fleet of relation databases, mainly MySQL services spread across more than 2000 nodes and on different DC's data centers sitting geographically far away, and we have to make sure that all of these services hosts which are running these services should be compliant as per the security patches, then firmware upgrade, kernel upgrade, and MySQL services upgrades like minor or major. So the thing was that, so initially when we started keeping our fleet up to date healthy, so we we're doing like manually with the use of some small automations with scripting and other things, but it was not scalable, and reporting was the problem, monitoring was the problem, following the same standards was the problem, everything. Then thanks to the Apache Airflow, which helped us a lot with implementing our business logic to upgrade the hosts. So let's talk about a simple use case where how we pick up a host in a cluster. As I said to you that there's a huge number of hosts, and how we pick them from each cluster, and how we make sure that it is successfully upgraded or not. First of all, when a DAG gets executed, a DAG is responsible for picking up a right host, which is eligible host. Eligible host means there are few criteria, like if it is running outdated version of kernel. Let's talk about kernel upgrade. And once we find out that it is running outdated kernel, and if it should not be in repair state. Like if somebody is already working on it, then we assign an attribute called repair. It should not be in repair, or it should not be in maintenance, or it should not be like if any backup is running on that node. So we take backup of each cluster-wide one backup. So we need to make sure that the backup is not running on that host. Once this criteria is checked out, and if we are true that this host is eligible, then we move ahead like so monitoring it. Unmonitoring is essential because if you don't unmonitor, a page will be triggered to the on-call person saying that a host has gone down. So basically, when we are doing kernel upgrade, we have to reboot the machine to pick up the latest kernel. So to do that, we have to unmonitor the host and wait for a couple of minutes so that it goes into snooze state, and then block IP tables, block from IP tables. Basically, we have LB. Okay, LB is responsible for sending all the requests to a set of hosts. So for example, in our setup, we have one master and multiple RO means read-only replicas, where only select queries are sent. If any application wants to get any data, it has to go through the LB, and LB is responsible to send that request forward to the idle or less busy host replica. So for that, we need to block, and LB will mark it as unhealthy or out of service, and it will stop sending the request. Once that is done, we move it to a host silence. Like it should not generate any matrices or anything. After that, the next actual step is that reboot. What happens if the reboot fails? If reboot is up, then we have to monitor, like it is coming up, it is booting. If it is up, then we verify that internal services are up or not, like SSH and MySQL service. If it is not coming back from the reboot state itself, then we have to make sure that we create a ticket for it so that the on-call person can take care of it, like debugging. And if it is a hardware fault, then it has to be sent to the hardware team, which is a site of teams, we call it, and data center team basically. And we do it basically all the machines. What we work in our organizations are bare metals. So we have to take help of the data center to help us out on the hardware issue if it is anything. Okay, no, that is a faulty thing. If it is good, then we have to verify as soon as the server is up. It should, talk to the master and take all the backlogs and keep itself up to date, like verifying the lags. We should verify the lag. If it is a lag is 0, then we consider that host is good enough. Okay. So once the lag is down to 0, then we unblock it. Unblock the IP table so that the LB should start sending the request to this host, and we monitor the host so that if something goes wrong, the on-call person can take care of it. Then we move it to managed state from the maintenance state, and then we remove it from the zookeeper. So there is one most important thing is that zookeeper, service coordinated, service coordination service. So what we do with this zookeeper is that in our DAG, we keep the host information, which host is picked up. Like let's say host 001, we have the DAG has picked up, so that the next replica of DAG, we are running it in multiple sequence. So the next DAG should not pick up the same host, and both DAG should not work on the same host. So that's the reason we keep a metadata into zookeeper. And whenever a DAG kicks off, it will check whether this host has been already in process or it is picked or not. If it is picked, then it will skip and it will go to the next cluster instead of the same cluster. Because if, let's say, the picked host goes down and in the next run, again, the same DAG picks up the next host and that also goes down. So we will have like ending up putting all the host into some dark side, and we don't have any healthy host to serve. So what we do, we pick only one host and we make sure that nobody is picked, nobody in the sense the other DAGs are picking the host from the same cluster. So we advise all the DAGs to pick it from some other cluster when one operation is going on one host in a cluster. So this is how the workflow works. As I told you about zookeeper, we are using it as a service coordination to keep the metadata of the host, which is in progress. And as soon as the host is successfully processed and it is back, and we make sure that that log for that particular host is removed, and it will go to the next host. And as soon as it picks the next eligible host, it keeps a metadata of that host name into zookeeper and proceeds with the further steps like unmonitoring, silencing, blocking from the IP tables, all those things. And how we are handling the alerting part and tracking. So we have a common tool, Slack, for our day-to-day interaction with the teammates and users. And it's a very good tool. We have found that for notifying any success or failures on any DAG. So we have integrated our DAGs with Slack. As soon as any host is picked up from the cluster, we send out a notification message into a channel, Slack channel, saying that this host has been picked up at this time and the reboot will be initiated in like 1 minute or 2 minutes, something like that. And apart from that, if something goes wrong, then we have a Jira software, which is a common tool for us to track all the issues and get update from the other teams. And we add that details like so-and-so host failed to come back online, and we put that information and we assign it to the current on-call person. And monitoring, we have like internal observability, where we have like exposing the matrices to that monitoring tool. Then this is the basic MySQL upgrade DAG. So here, if you see that there is a sequence of operations, and each circle is called as an operator. Operator can be a default operator, which is provided by the Airflow itself, or you can use your own operator. Operator is nothing but a function, Python function, you can say what you want to achieve it. So like if you see the first operator on the top is a DAG starting point. On the second circle is a custom Python operator, wherein it is making a call to a internal inventory to get a host for a reboot. So get a host means, as I told you, we have certain criteria to get the eligible host, right? So we get the eligible host from this Python function. Then we send it to decider. Decider will check whether that host is really applicable or not. If it is not applicable, then it will just skip it and it will go into back into sleep, or else it will proceed with the next step, like notify the start, which will notify the Slack initiate on Slack message, then on monitor, then wait for host silence, then it will put into maintenance, then setting up the attribute. So from when you're upgrading from one version to another version, you have to decide what is the version, right? So you have to set that version so that once we kick off the Puppet, yeah, I forgot about that. We use Puppet as the configuration management system, and Puppet will check for that attribute value, and we have inventory system, right? In inventory system, we attach an attribute called MySQL version, and Puppet will read out that what is the version I need to install, and Puppet will initiate according to that. If there is no change, it does nothing. If there is any change, then it will start processing all those required steps. Then once that is done, then we block the LB, then stop MySQL, run Puppet. This is where the actual run Puppet operation happens. And once the run Puppet is, so we have to run 2 times in our setup. One to actually pull all the required packages, RPM and other things. The second time is to make sure all the permissions, file system permissions and configurations are up to date. Then we are verifying here the MySQL binary, then actual start of MySQL, and rest of the steps remain same, except for notifying the success or failure. If in the end, if you see, we have like move to managed. From there, we have delete zookeeper log and notify success. And if it is failure, then we create a Jira and notify failure, but we are not removing the zookeeper log, so that next DAG should not pick up the host from the same cluster. We don't want that to happen, because if there is a problem with the configuration itself, then it will bring down all the hosts in the cluster. So we skip that. One host failure is the maximum affordable thing we can say for our MySQL services. So that's the reason we skip that particular cluster and we go to the next cluster. So similarly, we have for the kernel upgrade here. We have
quick time check. We are into the Q&A part. We just have right. 7 more minutes to complete everything.
Yeah, got it. Thank you. So here we have kernel upgrade. It's almost similar. There is no change at all, except for the reboot. In previous step, we had setting up the MySQL attribute and Puppet run. Then what are the benefits we got from this one? So the benefits is that earlier we had to spend a lot of time on doing the RTB and allocating resources for completing this RTB stuff. Now it's seamless. It's working in background, and it's keeping our fleet healthy. And before, it was very difficult for us to get the getting our fleet healthy. So now it is compliant with the security patches and other things. And spare nodes. So spare nodes are like the hot replacements, where you need, one host goes on, you need a host which is readily available and you patch in service. So that is one. And recently it helped us to upgrade from the open source to the enterprise version on all replicas. And it helped us with upgrading from CentOS 6 to 7, which was very good. It was very human effort we saved there. Then finally, we are here at the last stage where we can wait for your Q&A.
Thanks, Asif. Thanks.
I have one question.
Yep.
Using Airflow, when you are doing multiple host upgrade, were you able to project how much time it is going to take overall to upgrade a particular data center or a set of hosts?
Okay, with respect to Hadoop or MySQL?
Anything, any example?
Okay, for simple, if you talk about kernel upgrade, I can say that we have completed like in a week. So we have some sleeps also in each host, between each host upgrade. So for 1,000 hosts, it took like I think 7 days. I don't have the approx exact number, but 7 days it took for us for simple reboots.
No, my question is like, were you able to, approximately project some sort of like, okay, I will be able to complete this by 3 days. When you write a change management ticket or something like that, be able to tell like, when you will start and when you will end.
Yeah, so basically in our case, right, there are different clusters. So we have to work closely with the customer also. We have to find their window where they will afford like my master reboot also. So according to them, we first prepare the replicas reboots for kernel upgrade. Then we schedule a window wherein we fail over current master to new master, and we take that old master for reboot. So there is no exact timing, but it happens like you have to schedule a window for the master particular, but for other replicas, you can do anytime. So that's how we are doing.
In the case of Hadoop, we actually completed one run of upgrades, and then based on that information, we have been planning for next upgrades.
Hey Asif, I have one more question. Like with this kind of mass scale upgrades, like how do we prevent inadvertent triggers? Say I triggered it, I would like to roll it back or withdraw the trigger upgrades. So how do we handle this kind of like erroneous situations?
Yeah, so in case of, let's say you have configured incorrect parameters and you have triggered, then we reset back the parameters and we'll let Puppet to roll it back to the previous state of configuration.
Okay.
Yeah, so let's say from 5.0.27 to 5.0.32, you're upgrading and it failed for some reason. And we just set it to the old version, and Puppet will make sure that it is back to the old version and the configuration. If it is configuration related, if it is like, if you're asking me about the OS failure, then we have backups, Hadoop backups, replica backups, wherein you can, in one click, you can just restore complete data.
Okay. But my question was like more on the context of say I have submitted a request and I would like to withdraw it for some reason, like site assume like there has been a site issue and we do not want to do it at all. So in such cases, like how do we withdraw the submissions which have been triggered for the?
Yeah. So yeah. Okay, got it. You mean to say once you have triggered the DAG, how do we stop it if there is any issue? Right. Yeah. So you can do it in UI. So in UI, you can go and just pause the complete DAG. So it won't pick up any host. It will stop at the same time when you ask it to wait or pause it.
Okay. Yeah. Thanks, Asif.
Yeah.
So Asif, are you running the Apache Airflow in the Kubernetes clusters?
No, but I think we have one team who provide us support. They are working with other teams to provide that support. But for now, for us, our application, we are running Apache Airflow into Mesos Aurora cluster in a containers, not in Kubernetes. But in GCP, for other teams, they are exploring.
Okay.
May I add? Yes, we have Airflow running on GKE as well as Cloud Composer.
Okay. And how about one, like you said, as you said, like you put a metadata in Zookeeper. In case in just a rare case scenario, if the metadata not placed in the right and somebody, then how you will prevent this one not picking the host, another eligible host? Like in case if some corrupted metadata happen in Zookeeper, then How you handle
Yeah.
this? Sachin?
Corrupted in the sense Zookeeper service itself is down, you're saying?
Yeah.
So if we don't get the, so we have a check that if we don't get response from Zookeeper, then the service won't go ahead to next operator. So we stop there only.
So how you monitor this one? Like through the UI of DAG, either like how you will monitor this one? Like Zookeeper is not responding. Hello?
It turns into a failure step. We have a on notify email address of our team. Like at this step, the DAG has failed. And our email, in the sense, it will email to our Jira team and it will create a ticket for us.
Hey, Asif and Jeff, probably one of you can take up this question from Kamesh. He says that is my understanding correct that you are using Apache Airflow jobs as another layer of abstraction to run your Puppet jobs?
So in the case of Hadoop upgrades, we don't, during the upgrade step execution, there is no Puppet runs happening. For us, we maintain multiple versions of these upgrade Hadoop modules in our clusters, each server. So when a new version is released, the installation happens a long while before we actually proceed with the upgrade. But in the case of reverting or change, in that case, yeah, definitely we would need to set a version change in the configuration file and let the Puppet runs to happen.
Yeah, so for major or minor version change, we need to depend on Puppet as an abstraction layer, because that is the tool which helps us, and we are using it to upgrade our services or maintain our configurations. Yeah, we need to depend on Puppet for some stuff.
Cool. Looks like we had some great questions. Do we have any more questions? Okay, I don't see any questions in the chat window as well. So with this, like, thanks a lot, Jeff and Asif. It was a great insight about Apache Airflow and how orchestration is being built to handle workflow management platform. And the implementation walkthrough was really good. And in terms of the handling different streams of upgrade as well. So with this, like, we have one more amazing talk lined up from Myntra folks. We have Tanya Sharma and Mohammed Bashir. Over to you guys.
Yes, sure. Just let me present my screen.
Tanya, you are on mute.
Tanya, you are talking on mute.
Am I audible now?
Yes, you are audible.
Okay, perfect. So, so the topic for today that we'll be presenting would be Spire and OPA and how to address zero trust policy in a distributed environment. So we will just go with a brief walkthrough on what is Spire and OPA and how we are actually addressing the authentication and authorization problems in our environment. So for the speaker introduction, I am Tanya. I'm working in the platform engineering team since almost 2 years now. And I'll be walking you all over through the authentication component, whereas we also have Basit, who is also in the platforms team, and he will be giving an insight on how authorization has been taken care and how the implementation is done. So to start with, just want to give you some context about the cross communication, cross service communication that is exploding nowadays. The rapidly evolving dynamic environment of the public cloud enabled a lot of teams to deploy far more frequently. Say maybe many deployments every few months to many deployments per day, and even the ability to provision and deprovision the resources on demand has enabled the creation of very specialized and focused independent pieces of softwares, which we also refer to as microservices. So basically, all of this in turn has increased the need for identifying and accessing services across these deployment clusters, right? And when we talk about identification and accessing of services, this in turn is, we've seen how traditional methods are used for serving authentication and authorization. And there have been a number of cases where the long-lived service credentials might get pushed to public repositories or some platforms, and therefore it is a very makes all the applications and organizations ripe for theft. So now when we talk about what how we're identifying the services, the first thing that comes into our mind is again access control. Right now, access control access control requires a form of identity to possess with your services or your nodes in your infrastructure. And as we all know, right, the proving of an identity requires possession of a secret. So basically, once you start using these secrets, then again, there is a challenge of protecting these secrets. So as we all see, right, that all these solutions end up with the turtle all the way down problem. And to break this loop, we need to find the bottom problem or the bottom turtle. That is some secret that provides access to the rest of the secrets we need for authentication and access control. And yeah, I mean, as the organizations continue to adopt new technologies, one thing is clear, that there are large number of smaller pieces of software that wish to interact with each other. And therefore, it increases the number of potential vulnerabilities that an attacker can exploit. And so the traditional perimeter-based approach, where we attempt to build a trusted wall, cannot be relied upon. It is very difficult to implement in today's dynamic environment, and hence the need for zero trust security model comes into play. By zero trust policy, I mean that we cannot trust anything that is residing in our infrastructure, and we need to validate even the identity of the services or even the nodes on which our services are running. So now let's go to view the architecture of any organization, the backend architecture. There are cloud providers, data stores, backends, and then obviously backends are further have their CI/CD pipelines, their container orchestration systems that basically are responsible for launching the applications. Now, all of these applications, they can be API gateways, key management, or maybe some batch jobs that are to be run. So things seem pretty straightforward when we're talking about it, but they do get challenging when all of these components want to interact with each other. And that is where, don't you think that these microservices should have the opportunity to decide who gets to talk to them and at what level? So this brings us to the agenda of the talk here. And we will be mainly focusing on authentication and authorization. So I'm sure you all might know the basics of both of these terms, but just to make it clear, authentication here, we're talking about the identity of any resource. Who am I basically answers the question of who am I. And authorization, authorization deals with that. Do that particular identity has the access or has the privilege to access any of the resource in your environment. So we'll be talking about how we have been tackling these two, authentication and authorization, in a dynamic distributed environment, and that too in a decoupled manner. So again, now when we want to see how we've built a platform to tackle these issues, there were various design considerations that are to be taken care of, especially, say, for example, from resource types, right? We do not want to implement a solution just for, say, for example, REST and REST services. We want a solution that can be used by any of the resource types for any identity types, be it your services running in a container or in a VM. And even we do not want to limit it to any implementation language, right? The engineers should have the freedom to use any kind of languages to integrate with authentication and authorization. Now, another key important feature here is latency. So we cannot afford to have an authentication authorization decision to be made that is taking more time than your actual service rate, right? That is a total failure of the system. So that is why we taking all of these parameters into consideration, we came up with a high level architecture. We went through a lot of approaches, and what we decided to use after comparison is something known as Spire and Open Policy Agent, that is OPA. As you can see right here, we have our services running on either your nodes or maybe in Kubernetes. So we have introduced two more agents into it, the authentication agent and authorization agent. Now, the authentication agent is something that has been built using SPIFFE and Spire, and the authorization agent is built using Open Policy Agent, that is OPA. So let's see how the authentication is taken care of using SPIFFE and Spire. So just a brief introduction about what is SPIFFE and Spire. It is an open source tool that is also a part of the Cloud Native Computing Foundation. It has a lot of enterprises actively contributing to it, and it can also be used. It has been already been integrated with a lot of projects like Nginx, HashiCorp Vault, even the Envoy proxy. So let's have a deeper dive into what are the major key points we will be talking about in case of authentication. So as I mentioned, right, whenever we talk about authentication, what is the first thing that comes into our mind? That is identity. Now, we need a system to provide identity to our service. And not only the service, right? As we just talked about how in zero trust security model, we can't even trust the node on which our service is running. So that takes us to another point of providing the identity to the node where our service is running. And definitely, we need a mechanism to verify and validate the identity of the services interacting. And since we cannot afford to have long-lived credentials, we need to have a mechanism for handling the expiry and rotation of these identities. So basically, all of these points, all of these are the main, points to be encapsulated in authentication, and SPIFFE and Spire is helping us to strengthen the identification of the software components. Now, let's move on to just a few basic SPIFFE key concepts that you all might need to understand for understanding the flow. So first is the SPIFFE ID. So SPIFFE ID is basically a standard format for a service identifier, right? Now, that means that the standard format for identifying services in your network. It's like this URL you all can see in your on your screens. Now, this trust domain, right? It can be it is basically unique to your organizations. So we use this SPIFFE ID to identify our services. Now, the second term that here that we need to understand is SPIFFE verifiable identity document. That is SVID. So these are basically cryptographically verifiable documents asserting a SPIFFE ID. Now, by cryptographically verifiable, what I mean is that these are actually X509 certificates and even JSON web tokens, and both formats are supported in SPIFFE and Spire. Now, moving to trust bundle. Now, what is a trust bundle? You definitely need a set of public keys to verify an identity that has been shared with you, right? So that is what a trust bundle is. And you can assume it like kind of like a root certificate bundle. And here it works for both X509s as well as JWTs. Now, the next component is the workload API. Workload API is one of the most important concepts here. And it is a local API where your services or your workloads can retrieve these SPIFFE ID, SVIDs, and trust bundle. Now, we might have a question here that why do I need to retrieve them instead of storing them statically, right? So the whole idea is that we are constantly updating these SVIDs and trust bundles. That is, they are being constantly rotating under the hood. And that is why we have the need to retrieve them from the agents. I hope these concepts are clear to all of you. Now, moving on to how we are securing microservices communication in our platform. Now we have the first step is to set up something known as the Spire server. So the Spire server is a centralized server that is responsible for digitally signing all the SPIFFE IDs that are present in your platform. That is, it is responsible for providing the SVIDs to your services. Then it is also responsible for attesting the node on which your service is running, right? So if we have to see right now how these SVIDs are communicated near your services, they are taken, that all is taken care by the Spire agent. Spire agent is something that provides all of this SVID, trust bundle, SPIFFE ID to your service. It gets all of this from the Spire server and it provides to the service. Now, how they are actually communicating here is that, say, for example, my service A wants to interact with service B. Now, my service A will acquire its SPIFFE ID and even the SVID from the Spire agent using the workload API we just talked about in the last slide. And it will be sending it to service B. Now, service B needs to verify that the identity I just got is valid or not, right? Now, this service B also connects with its Spire agent and verifies that the identity can be trusted or not. So this is how we are actually securing microservices communication in any platform. Now, moving ahead, I will just cover few of our, key adoption methods that we had used. So you can definitely go through the available blogs for SPIFFE and Spire, and you can see all the plugins and all the methods that are there present. I'll just throw some light on few of these that we've adopted in our organization. So the first here is node attestation. So we saw that, right? Even the node on which the service is running cannot be trusted. So Spire supports a variety of methods to attest your nodes. And these, include cloud selectors for attestation, like Azure, AWS identities, GCP, GCE tokens as well. So in our case, the cloud that we have is Microsoft Azure, and we are using something known as the managed system identity to attest the nodes. Now moving to how do we want to handle heterogeneous environments, right? We might have services running on VMs, we might have services running on Kubernetes. So we can actually use the same Spire server cluster, and for both of our environments, there are a lot of plugins available to support heterogeneous environment in your production in the organization. Yeah. So next comes the service interaction with these Spire agents. Now, as we just saw, that we can use workload APIs to interact with our Spire agents. Right now, by workload APIs, for workload APIs, we have available support libraries for Golang as well as Java. And for other languages, we can directly create a gRPC client to invoke the APIs exposed by the agents. So all of these things are, few primitives, deployment primitives that are being done. You can also adopt. So now next we want to talk about, say, maybe how can we scale this infrastructure. So there are a lot of methods you can have, say, for example, a single trust domain, or a nested architecture, or a federation architecture, right? So the decision actually depends on the kind of production environment you have at your organization. So the next thing that comes is registration entries. So the registration entries are basically the entries for each and every service in your organization. And we have actually automated this process of registration entries in our infrastructure. Now, we even have a BCPDR topology that has been set up where, whenever any disaster happens, we can immediately switch over to use the DR topology. So these were just few points that maybe can, you can keep in mind while adopting it. Another thing that to consider here is that there can be some amount of latency that might arise due to the addition of this entire flow. So we have implemented something known as local SVA caching as well, where even though your Spire agent is caching few tokens in the memory, but if you want to reduce it further, you can actually cache these tokens in the client process. And even so this caching, right, this has to be done only for before your TTL of the actual SVID expires. So in the background, you might also want to refresh it. So these are few tricks how we manage to reduce the latency for our environment. Now that was all for authentication. Now Basit will be taking us over how authorization has been built on top of SPIFFE.
Okay. Hello, everyone. My name is Mohammad Basit, and I'm part of Tools and Platform Engineering team at Myntra. So I'll be covering authorization part. So first of all, am I audible to everyone, right?
Yeah, Basit, you're on.
Okay. Okay. So I will be talking about the authorization problems and how we are addressing these problems. So before that, let's have a look on some facts which on what happens when authorization isn't done right. So these are some past incidents, and these are results of improper authorizations. For example, Facebook releases some too much of your information to your contacts, and second, we have some hospital releases a lot of health record as well. So these are all some authorization problems. So you can understand what happens when authorization isn't done right. So now let's move ahead and see what is authorization. So as authentication is done, identity of the client service is authenticated, proved. Now we want to check whether the calling service has the given permission or not. So for that, we have authorization. We can define authorization as a process through which any server can determine if the client has the permission to access its resource or not. So for us architecture, we have a lot of microservices. So let's take two service A and service B. Service B wants to interact with service A. So we need some mechanism or some system through which can check if service B has the required access or not. So for that, we need a authorization system. This is our problem of authorization. Now, moving ahead, we can generalize this problem in terms of three parameters, C, R, and S. We need to find a way to define and enforce some rules that can solve for a client C, which want to access some resource R of server S. And we want to solve it for all combination of CR and S in our ecosystem. So as you all can imagine, in a infrastructure which have a lot of microservices, will have a lot of combinations of CR and S. So solving this is a big task, right? So we will see how we are addressing this problem. So these are some problems which we are going to address. First is policy definition. We are giving a platform to users and service owners to define some policies for their service. Second, policy enforcement. So policy enforcement is always a painful and costly task for the service owners and for the application, because maintaining policy decision and these rules for allowing which service to access resources in the application code is not a good way, and it's also very uh, inefficient. Yes. Next, platform agnostic. Ours authorization system, which we are providing, will be agnostic to the platforms. Like the services are running in different platform and different environments, so it will take care of all platforms. Next, we have decentralized system. So the platform authorization platform we are providing is decentralized, as you also in the high level architecture design that we have introduced two agents which are taking care of the authentication and authorization. So we don't have any centralized system which will do this task for all the services. Next, moving ahead, how our authorization system works. So we mainly have four components. So through this high level diagram, if you see, we have engineers or service owners who need some user interface to define policies. And once these policies are defined, we are storing it in safe database MongoDB. Now we need a component policy distributor which distribute these policies to the nodes, different nodes where services are running. Now, if you see in the green box, we have service which is being called by some other client service, and we have installed two agents there, OPA and Aussie agent. I will tell in deep about these agents and all other components in detail in the coming slide. So these two agents will do the authorization check for the service. Moving ahead, so start with the first component. We have policy definition. So for policy definition, we are providing a portal to the users and service owners to create policies for their services. For example, you can have a look at an example of policy. We are asking users to define the resource path, its request method, and SPF ID. SPF ID has a general format, so it will be fixed. So we are just asking the client service name there, to which service we allow this particular resource path. So on this portal, we are also providing options to, we are allowing these operations like addition, modification, and deletions of the policies. Third is capture of intent. So this platform that we are providing is a self-serve, and as we all know, like whenever anything is self-serve to users, we are kind of tend to make some mistakes. So we are providing freedom to the users, but not enough to make some bizarre mistakes. So for that, we have an approval flow for these all these requests. Next, we have a policy distributor. So this is an in-house built service which will be responsible for distributing policy. So now in the previous slide, we see like policies are defined. Now we need some mechanism or some service which can distribute these policies to this service node where authorization will take place. So we have policy distributor which fetches and checks regularly for the latest policies, if any added by the user, and update it in Redis cache. We are using cache here for faster response. Now, whenever suppose there are different nodes, like as you can see, there are 3 nodes on which Authy agent is running, which will call this distributor and fetch the latest policies for the service on which it is residing. Like for in the first the first one, Authy agent will fetch fetch all the policies for service 1 only, and policy distributor will respond with the policy template. Now, what more task policy is creating this Rego. Like our OPA, which we will be using later, is work on the Rego. Rego is a declarative language. So we are defining policies in a code form, which will be in Rego code. And policy distributor is creating these templates, these Rego templates, and sending it to Authy agent. Policy distributor is also running, is a centralized system which is running in high availability mode. So we can scale it as, we scale it also. And yeah, so that's all about the policy distributor. Now coming forward, we are using OPA engine. OPA is an open source and is a cloud native computing foundation project for advanced authorization. It's a general policy engine that unifies policy enforcement across any tech stack. So when I started with the authorization, so some problems which we were going to address. So among that was one was policy enforcement. So OPA handles this problem. OPA is local hashed cache, and means it is caching these policies which are written in form of code in Rego, and storing it in cache for decision making. OPA provides third point is OPA provides high level declarative language. So yeah, it works on the Rego language, and it also exposes some APIs to update these policies and to receive requests for making decisions. So our enforcement issue problem is being solved by this OPA because it is running parallelly to the service and maintaining and making the decisions and storing these policies. So services don't have to hard code anything in their code. Now how OPA works. So if you see on the right side diagram, there's an OPA having some policy and some data using which it will make some decision. Now service sends some service is being requested by some client service now, and then service will send some query to OPA, and OPA using these policies and data will make some decision and respond to the service. You can have a look on some input like a structure, how input structure will look like, and the Rego policy template you can see. So in input we are sending 3 things: the method, resource A, and SPF ID. So this is so the SPF ID the service got after authentication. in authentication process, and will send the same SPF ID to Aussie agent for making authorization. Now, moving ahead, we have introduced Aussie agent. So in the previous slide, we saw like service was directly calling OPA. So when service like do the updation of policies and other things, and also calling OPA, like it's then again depends. We will have some dependency on service for like regularly updating these policies and everything. So for that, we have introduced an agent, Aussie agent. This is an in-house built service which will act as an interface between service and OPA. So instead of service directly using OPA, it will call Aussie agent, and Aussie agent will consult the OPA to make decision and will respond the same response as it get from OPA to service. Also, Aussie agent will run in the same environment, so all calls will be local only. And one more task Aussie agent performs is that it will fetch the latest policies from policy distributor. So yeah, these are some tasks of Aussie agent. So there we completed how our authorization system works. Now let's see some key highlights of our authorization system. First is we are doing caching for faster response. So services which are using this system authorization platform is also doing some caching for the response it got from Aussie agent. Like suppose if same service calls again for the same resource path, then it can allow it faster. Second, we are supporting multiple resources type. So as you all might have seen in the design consideration, like we are not only supporting REST-based API services, we are also supporting gRPC and some other resource types which are implemented in different services having different custom-based libraries. Third, we are supporting different formats of query params. So resource paths like URLs contains query params as well. So we are performing authorization check at a granular level for the key value pairs which are represented in form of query params. Next, we are also supporting BCPDR, like disaster recovery plan, business continuity plan for disaster recovery. So
Basit, general time check. We have 2 more minutes actually, and no query.
Okay, so moving ahead, we have this sequence diagram. So service 1 calls service 2, and service 2 will contact its agents to make the decision. First, it will contact authentication agent, and once authentication is done, service 2 will again contact Aussie agent for making the authorization check. This is a sequence diagram you can see. Now next we have Tanya, next slide. Yeah. So these are some points which you can plan for production rollout. Like we have introduced new Authentic flow on top of without disturbing the previous flow unless the whole system becomes stable. So this will help us a lot. And second, we are passing this JWT token in authentication under the authorization header. So we are using a bearer scheme to pass this header to support backward compatibility for some services which are already using this header. Third, active monitoring and alerting. So our agents, so just imagine a situation where these agents are running, and what happens if these agents are down. So we need some monitoring. We need active monitoring and alerting on these agents. So for that, we are using our in-house alert managers and monitoring tools. Next, we have, and next slide, yeah. So these are some future tasks on our roadmaps. Like we want to enable our Authentic for TCP connections, SSH connections, also for messaging system like Kafka, RMQ, and data stores and Azure Blob. So these are that's it from these are some tasks we are planned. So that's all from our side, and now we are open for questions.
So I have a question, Mohammed or Tanya. Like, say, assume like there was a network partition and the host rejoins the network. In that case, like how node identity is being validated or how it's been revalidated?
Sure, I'll answer to this. So what happens in case of node attestation is that your cloud platform is responsible for giving the identity, right? So in our case, say for example, we are using Azure MSI as an identity for it. So whenever an agent comes up at the start, the first step is of node attestation. So I think it fetches some kind of token from Azure, and then that token is sent to your Spire server, and then that Spire server again verifies from Azure that the token that I've got is valid or not. So in case where your host went down, right, and has rejoined your network, say for example, its identity will be the same in your cloud. So that is how whenever the agent comes up again, it'll again start for a fresh attestation. And if that node is part of your cloud and the you know it has its own identity. So now that MSI I'm talking about, managed system identity, is static and it is unique. So in that case, it will again try to prove its identity using the same token from your cloud. So that is how it all is being handled.
Okay, okay. And I have one more follow-up question, like how the trust bundle is deployed or bootstrapped in a secure fashion?
So basically, the Spire server is responsible for sharing the trust bundle to all its agents, right? Now, nobody else is actually, I mean, your workloads are not aware of the trust bundles. So whenever the agent starts, after when the node attestation has happened, the second step is when the trust bundle is loaded. So in a case where the node attestation or the node identity is not valid, we will not have the trust bundle loaded in those cases at all.
Okay, okay, thank you.
So, firstly, I have a query. Like as you said, you have a lot of microservice running based on authorization and authentication. Service A want to talk to service B, then service B go check authorization and authentication. In case like if something went wrong with your authorization, then would you put any timeout to the service A, because cascading effect will impact your overall system, correct?
Yeah. Okay. Yeah, Tanya.
Vasit, you want to answer this question?
No, Tanya, you can go ahead.
Okay. So you're talking about in case anything goes wrong, right? Yeah, definitely. If so, basically we give the flexibility to the engineers, to the owners of the microservices, to add the policies. So if anything goes wrong in adding the policies, right, I think the best decision lies in the hands of the owners of the microservices, to which policies they want to allow, which policies they don't want to allow. So I think that is one check that we are taking care of, that leaving it to the owners. Then second check is that we can always have a fallback mechanism, as we saw that we have enabled a new flow for authentication and authorization on top of the existing scenario, so that anytime any mass failure happens, we can always revert to the existing flow where authentication and authorization is not happening. So until and unless all the systems get back to stable state, we will not have any service. Service downtime will not be there due to such cases.
Thank you.
To add to that, to add to what Tanya mentioned, so apart from having a switch flag, if anything goes wrong, we always fall back to the previous flow. We have another health check implemented where any application on any host does not mark itself up unless the authorization components are up. So anytime, let's say, authorization components goes down, so that particular instance of the service will also mark itself out of service. So that is how we are also, preventing the cascading effect.
Yeah, probably on the same context, I have one more follow-up question. Like, how instant is the propagation say when we downgrade or revoke the authorization in like kind of large scale machine? Any timelines as such?
Sorry, can you repeat your question?
Yeah. Say for example, we downgrade or we revoke some authorization roles. How instant it is in terms of propagation to like large scale nodes, say 1,000 nodes or something like that? How instant it is?
Okay, so Basit, you want to take it or should I?
You can go ahead, Vivek. Yeah.
Okay, so for now, our policy refresh frequency is set at 30 seconds. So again, that is a tunable duration, like time interval. Apart from that, that is the interval at which it will try to update the policy. And once policies are updated from all the clients, it is instant in parallel, basically concurrent request which goes to policy distributor. So it will become effective immediately after 30 seconds. So it just depends on the initial frequency which we have set to 30 seconds. It can be increased or decreased.
Okay. Thanks, Vivek.
So Vivek, I have a follow-up question. Say, as you said, authentication authentication provide a flexible way of authenticating your services, microservices together. Don't you think this is the overhead running on top of your microservice, because spare server running outside of your Kubernetes cluster, agent running inside your Kubernetes cluster? What do you think? Like, this is not an overhead of your microservices?
Basically, you are saying the overall network latency or the response time getting impacted because.
Yes.
Okay, so to answer that, all your authentication and apart from initial authentication, all authorization is handled locally by the Spire agent, which is running on your local box. Like every service box will have one agent running on it, and all the communication is over gRPC, which is again very fast. Plus, additionally, to handle it, we have also implemented the caching mechanism, which Tanya talked about. So generally, your application should cache the the tokens within the application. So call to agents will also be very limited. So that is how we have handled the overall latency and the response time.
Okay.
So one thing to add here is that none of our microservices have to make any external calls. Everything is being taken care by the local agents there, and only the background activities of updating the policies or everything that is where the server comes into picture. So in terms of overhead for the microservices, we've that is very minimal, as in no external calls for these decisions at all.
Right.
So
And,
that is benchmarked under single digit of milliseconds.
right.
So this question is always be there. Overhead will always be there in security, but it's always about securing versus unsecuring. Definitely, overhead in a couple of milliseconds is okay and acceptable. So I believe these agents supports two way of local host communication. One is TCP layer, other is at the Unix socket. So currently we have implemented use Unix socket, which is I think acceptable limit of less than 10 milliseconds. I think it's the 1 millisecond or
yeah, generally as per our NFR, it is like 1 or 2 milliseconds, and that
if
too
we
only
go
when
implement if you implement Unix socket, I think it's in microseconds. I think microseconds.
Prem.
Yeah, cool. Hope we are done with Q&A. Thanks a lot, Tanya, Mohammed, and Vivekanand on Spire and SPA. It was an absolute finger breath talk about authentication and authorization, indeed with critical design consideration. And it was really a great showcase of how a disaster could be with the inappropriate authentication and authorization at every possible tier while dealing with bad actors. Thanks a lot, guys. So with this, like we have, yeah, sorry, go ahead.
Thank you.
Good. So with this, like we have one more amazing talk by Dipanshu, who is going to talk about how to deal with operational events, metadata store with the large scale volume like LinkedIn. So with this, like I hand over to Dipanshu. It's over to you, Dipanshu.
Let me just quickly share my screen. All right. Everyone is able to see my screen, right?
Yes, right.
Cool. Just let me know if there's any problem with running the presentation. All right. I'll start in that case. All right. So hi, folks. Today we are going to discuss a scale tail. It's a case study about migrating a monolithic data set to a distributed system with 50x write capacity. I'm Dipanshu, and I've been with LinkedIn for close to 4 years now. Here, I work with the capacity engineering team that is responsible for the capacity and efficiency of the overall LinkedIn site. Let's get started by talking about what Informed is. LinkedIn's products consist of a myriad of interdependent services, which are in turn supported by many underlying infrastructure components ranging from physical hardware to software services and platforms. And operational events which directly or indirectly impact the site or its ancillary services occur with great regularity, and many of these events produce useful metadata. Informed is a system for storing and consuming the metadata about operational events at LinkedIn. And these events could be, deployments, A/B test activations, etc. It has a powerful querying interface to discover and troubleshoot issues, and it consumes more than 40 different event types from producers from across all our environments, like production, staging, the grid environment, etc. All of this is stored in an ACID-compliant MySQL backend. The data in Informed grows at a very fast pace, almost like 17 million events a month, and it keeps on increasing. Each event inserts data into at least 10 MySQL tables in under 100 milliseconds while being completely ACID compliant. And even with this volume of data, it provides a very efficient querying interface with complex queries across tens of millions of events returning in under half a second. And since it is heavily used across engineering, the downtime for such a system can be quite expensive for the company. Events are the basic building blocks of Informed, and each event is of a particular type called its event type. This builds on the object-oriented programming constructs, right? How you have a class and then you create an object of class. So similarly, event type can be considered a class, and an event is actually an object of the class. And the major event types are, deployments, traffic shifts, A/B activations, etc. And every event type has its own schema, with each schema having like multiple fields associated with it. These fields that are present in the schema are called elements, and there are over 150 elements in Informed right now. An entity is an object of an element that is associated with an event. So how an event is an object of an event type, similarly, an entity is an object of an element. And since an element is bound to an event type, an entity is bound to an event similarly. The event has a start and end time, which allows us to represent the timeline over which the actual event happened. So consider something like deployment, right? A deployment would start, it would be, when it starts, it would be in the queued state, then it would go to probably in progress, then deploying, and then it will have like a final state, which would be, succeeded or failed. So that is a timeline over which this event happens, and it's not point in time. An event with a null or zero end time hasn't ended. So basically it's still in progress and it is still mutable. So it can transition from, let's say, in progress to deploying to succeeded or failed, something like that. And this is an important detail that forms the basis of successive schema and data migrations that we're going to talk about. Once the event has ended, that is, it has a null and non-zero end time. For all practical purposes, it is immutable. Again, like a very important detail that will help us in the schema migrations that we'll talk about later. And an immutable event can be migrated between platforms without risking its data integrity, because it can no longer be changed at the source, right? So here's what an event looks like. Here's the schema of an event. It has an ID. It has a name, which is the event type of that event. It has a start at timestamp. It has various entities which have, the name of the element, the exact value, and the type
of that element. Type could be like string, integer, float value, boolean, etc. And finally, it will have an ended at timestamp again. Events can also have sub-events. It is basically a one-layer nesting, which is like, an event can have a sub-event, like a deployment can have a sub-event, like host deployment or something like that. And to store all of this data, Inform leverages the entity attribute value model. And all of this data is stored in MySQL in that way. So, and the EAV is an efficient storage model that optimizes for space while allowing document store and graph database like flexibilities with native MySQL data types. This is what the schema for Inform looked like more than a year ago. Every event was stored in the event table, with every unique entity only stored once in the respective entity table. And the entities were linked to the event via the event entity mapping table. This mapping table has the event ID, the entity ID, and identifier for the element that the entity is an object of. So any lookups required multiple complex joins across event, element, and multiple entity tables. So while we were storing lesser data with this schema, we were spending significantly more time querying it. And between CPU cycles and disk storage, one is obviously much cheaper than the other, even in the absence of spinning disks, right? So at the time, Informed was consuming about 200,000 events a day, and the overall data size was a little over 2 billion rows. And at the time, we were expecting a 10 to 15x growth over the next 2 years. But the MySQL instances that we had were already buckling under the existing load. So initially, the Informed service data was hosted on a cluster which had a traditional MySQL topology with a primary and a replica, and which also hosted other tenants in the same cluster. So it was co-located. This caused resource contention on the host, and Informed being a very active service, the instance was not able to scale, and other tenants were actually getting impacted because of it. So we moved the Informed MySQL schema to an independent host and beefed up the OS resources to vertically scale it out. But then it in turn triggered scaling issues with the replication, right? Since replication in MySQL is traditionally single-threaded, the replica was just unable to keep up with the number of writes that we were making on the primary. So this added to the write scaling issues, and we were always at a risk of losing events in case the primary ever failed and the replica was still lagging. And since there was also the projected growth for the Informed service to be more than 12 terabytes, which obviously cannot be sustained on a single node, right? Because the MySQL nodes that we have at LinkedIn are a standard 3 terabyte configuration of disk. So all of this also added to the data scaling issues for Inform. So the answer for all of these scaling was sharding the data and the writes. And here are some of the approaches that we thought of. So there was obviously application level sharding based on regional or fabric specific, so that we can distribute it across clusters or have the logic built in within the application to shard the data across the cluster. But this required a lot of application changes, and mainly the application had to be shard aware basically. And the Informed team also needed the data to be accessible from one portal instead of having it distributed across standalone MySQLs and having to be mindful of how to query the data every time. So this was not a viable candidate for us. Then we thought of the MySQL NDB cluster or InnoDB clustering service, where we can have multiple MySQL nodes as part of the cluster and have handshake between them to sync data to each other so that write scaling would be possible. But the problem here is again that the disk usage is a static value and cannot grow beyond a certain threshold. And also that MySQL NDB is an enterprise paid service, so which is definitely not cheap to implement. So we were looking for a logic which will help keep the application changes to a minimal, and still we could leverage MySQL as back for sharding purposes. So finally, what we decided on was Vitess. So in simple words, Vitess is an open source sharding middleware for the MySQL infrastructure. It helps scale massively at sometimes thousands of nodes and millions of QPS. Right? And Vitess is a proven technology that was built for YouTube to scale their massive connections and writes. And for a service which needs transactional capabilities and sharding, Vitess is a very good option. So both of the things that were a prerequisite for Inform. Good part about Vitess is that it is built on the MySQL client for connectivity. So the application connects to it the same way as it would connect to a standalone or a traditional MySQL instance. But behind the scene, Vitess has a large ecosystem of services running to manage multiple nodes and the routing logic, etc. So this is great because we do not have to make too many application changes to onboard to the Vitess platform. And Vitess also has a very good query rewriting interface that allows it to tune incoming queries to be more shardware so that it can improve the query latency. So since we leveraged the EAV model, our data was heavily normalized and lacked a sharding key that could be consistently used across all our tables to move them over to Vitess. A shard key is basically a unique identifier used to partition data such that all tightly coupled data is stored on a single partition or a shard. Since we store all entities only once, it was impossible to store most of them on a single partition, as a single entity could be bound to multiple events. And as most entities would map to more than a single event, it would form just a complex web of many to many relationships. So we had to flatten the table structure a little. So we had to denormalize the schema to have a common shard key. So this required removing the mapping table event entity and storing multiple copies of the same data in the entity tables for individual events. And each of these rows would be linked by the events identifier. So this made sure that we could store all the data related to an event, that it's the event itself and all of its elements and even the sub-events on a single shard. So all the data required to query the event was either on disk or in the best case in memory, which enabled local lookups and inexpensive aggregations, that is scatter gather by the Vitess framework itself. It definitely increased our storage needs, but dramatically improved the scalability and performance of our data store. And again, like between lesser CPU cycles and network round trips versus lesser storage, the former clearly beats the latter, right? So this is how we imagine the new schema to look like. So instead of joining on the entity tables on the event entity mapping table and then onto the event table, we could directly join the entity tables on the event table. So this helped eliminate multiple index lookups and any disk access for temporary tables. And while we could shard our data by any other key like the event type, API key, etc., it wouldn't guarantee that all the data of an event is locally available. The newer model also required more joins on the entity tables, but they were significantly less expensive than the hierarchical joins that we were doing earlier via the mapping table. So the schema migration was a one-time activity to denormalize the tables and then prepare them for sharding at the same time. Since we had a few lookup tables that would mostly store the internal metadata, they couldn't be sharded, right? Because they did not have something like an event ID or something. But however, something that we realized was that maintaining two different schemas or like key spaces is generally going to be an operational nightmare for us. So what we did was basically we fake sharded these tables. So fake sharding is nothing but assigning them an arbitrary shard key and predefined value, so that ensured that all of this metadata lives on a single shard, and it is replicated to like whatever the replicas for that shard are, right? And the application logic had to be carefully altered to ensure that these tables were actually never joined on the other sharded tables, because otherwise it would result in cross key space joins, which again could be expensive. However, like all these sort of fake sharded tables could be joined onto each other because all of that data lived on a single shard, right? And we also removed any sort of foreign key references, letting the application logic manage these relationships. But all of this wasn't without any challenges. So we had to migrate over 2 billion rows of data while reading the data from the old schema and writing it to the new one. And all of this was done on the same database. So the application had to understand both schemas when writing events and while querying them. That is, we need to ensure backward compatibility. We had to optimize the queries for both the schemas since we were querying twice for the same data while the migration was underway. So that also increased the load on the database, not just for the writes, but also for the reads. And all of this had to be done with zero downtime, right? So how did we do it? So if you guys remember, we discussed the concept of event immutability earlier. So that actually forms the basis of this data migration. Since an event once closed cannot be altered at the source, it offers us an opportunity to atomically migrate it from the old schema to the new one. So we would read closed events stored with the old schema in batches and translate them to the new schema while cleaning up their references in the mapping table and the old schema. And all of this would be done in the scope of a transaction, making sure that the events are atomically translated and the operation is idempotent. So that is, if the same batch is erroneously processed again, it would basically result in a no op, right? And this ensures we have the right data consistency during the migration and even after that. And this workflow was run over a week, and it successfully translated all the 200 million plus events that we had at the time to the new schema. And while this was necessary for the eventual move to Vitess, this exercise was also an opportunity for the Inform team and the data SRE teams to build confidence that a data migration of such magnitude could be done without any downtime. And with the migration done, this is how the schema looks like today. There's no event to entity mapping tables. All the rows in the entity tables store their own back reference to an event and are resolved the event with the help of event type schemas. The new schema has been, battle tested at a scale greater than 6 billion total records. And this pilot has been ingesting over 500,000 events every day. And we have revised our growth projections now to over 50x over the next few years. So we store a lot more data right now, but we make up for that and more with the optimized queries and massive scalability that we have with the new schema and the success of Vitess migration that we're going to talk about. So with the new schema in place and all the data migrated, we were ready to get on the Vitess rocket ship. But this wasn't as dull as we had hoped though. So we had rewritten most of our MySQL queries to be heavily optimized, and some of them were not compatible with Vitess. An example of that would be how we compose events for a search response. So once we are able to do complex joins over tens or sometimes hundreds of tables to get to the list of events that match the user's query intent, we have to compose each of them by fetching all of the associated entities, right? So on an average, an event will have approximately 10 entities associated with it. And if we compose every event serially, we'd at least fire 10 select queries, assuming that the event does not have any sub-event, as every sub-event would require at least 10 of its own select queries for composing it, right? So for the 1500 events in a search response, which is the default query size that we have, even with 10% of the events having at least 3 sub-events associated with them, that's a little less than 20,000 queries for a single search request, which is clearly unsustainable, right? So since we only have about 150 or so elements and hence the same number of entity tables, what if we could query the required entity tables exactly once for all of the events, right? So even in the worst case, that's 150 queries with no cap on the size of the actual query. And what if we could merge all of these 150 queries to a single query, right? So in the real world, though, there are limits on the query size, and the default limit for the query size is capped at 16 MB, although it is configurable. So for this very purpose, what we end up doing is we union the select queries from various entity tables and batch them together while keeping the size of the query sent to MySQL under 25 MB, which is the configured query size limit for our MySQL cluster. And while this optimization saves us like millions of queries a day, it was clearly incompatible with Vitess because it required cross key space querying, right? So to ameliorate this and for this specific optimization only, we implemented a parallelized scatter gather approach in our application that is informed to query each chart independently with this exact query and collate the results within the application and then compose the events. So this made sure that we do not compromise on the search performance and are still able to leverage all of the goodness that Vitess has to offer. We did similar optimizations for other queries, and in fact, at the time had about like a 20+ page document to list, test, and optimize every single SQL statement used by any of the informed subsystems. And also to add to this fact was that informed was our first Vitess setup on an infrastructure. And this created some tension, right? As we had to make sure that we have all the bells and whistles that take care of the cluster and especially the monitoring and the team onboarding. So we were able to build that whole infrastructure around it to support it. And another big challenge that we had was data migration. So since at the time Informed was already consuming about 1.2 terabytes on the native MySQL instance, and there is no easy way for us to migrate the data from native MySQL instances to Vitess cluster without causing a downtime. We had to think out of the box. We had to like figure out an out of the box process to plan a migration with very minimal downtime. And initially we thought we could stop the service, dump the data from the native to the Vitess cluster. But when we tested it out, like during the tests, it took us more than 2 days to actually complete this. And we tried this in staging. And so it wasn't just a snapshot copy, but it had to be like batch copy. We had to batch copy the data individually so that the data gets sharded across the Vitess cluster seamlessly. And this was not an option for us, right? Because we clearly could not afford a 2 days worth of downtime. So we had to get creative here. So before we delve into the migration and the migration techniques, I want to give you a quick overview on the Vitess components so that it will sound familiar when I speak about those components. So let's start from the bottommost layer where we have multiple MySQL shards where each of them stores a subset of data. And each MySQL node has a proxy service running with it called VT tablet that communicates the health and the role of the underlying MySQL node. And it also communicates with the topology server, which stores the routing metadata for Vitess. Topology server is the heart of Vitess and is a distributed data system. We use HCD for the service, and it stores the routing metadata and also the Vitess topology metadata. This service helps Vitess to route a given request to the right MySQL shard. On the right side there are these processes called VTCTL and VTCTLD, where VTCTLD is a command line operator for managing Vitess topology, and VTCTL is the graphical user interface for cluster management. The main client interface is VTGate, which is a stateless proxy that helps route the application request to the respective MySQL shard by a topology server. Topology server metadata is very small, so most of the time it's just cached there until there is a change in it. So the client request flow is something like this, right? A request is made to the VTGate. VTGate checks with the topology server and routes it to the respective VT tablet process that in turn passes it over to the MySQL instance, and thus goes the response back to the VTGate process from where it is served back to the client. VTGate process is where Vitess also has a query rewriting logic so that it makes the query shard aware. And so the query plan used for Vitess would be slightly different from the traditional query plan that we get on a MySQL, like a standalone MySQL node. So for this reason, again, we validated all of the SQLs that are used by any of the subsystems of Informed to make sure that the query plan seemed good and rendered good performance. Other aspects of it are key spaces. So key space is synonymous to the schema in MySQL. And the key space ID is the value that is used to decide on which shard a given row lives. For example, we use hash values for sharding. Then each hash value is a key space ID, and each shard covers a range of key space IDs. VIndex provides a way to map column value to a key space ID. And this mapping can be used to identify which shard contains a given row for a table. A table can have multiple VIndexes, and this is just similar to the indexes in a normal MySQL table. But the primary VIndex is the most important for a table, and it is analogous to the primary key in a database. Every sharded table must have defined like at least one of them so that it can be distributed across the shards, right? And conceptually, primary VIndex is similar to a NoSQL sharding key. The uniqueness for a primary VIndex does not mean that the column has to be a primary key or unique key in the MySQL schema for the underlying shard. So you can have multiple rows that map to the same key space ID, and the VIndex uniqueness constraint only ensures that all the rows for a key space ID end up in the same shard. And finally, we have the vSchema. So a vSchema allows you to describe how the data is organized within key spaces and shards. And this information is used for routing queries and also during resharding operations. So the migration techniques, right? We had a few challenges for planning the migration. And some of the techniques that we considered were, so the first was vReplication or vStream. So Vitess internally has these APIs that could be used for data migration from one cluster to another with zero downtime. And we thought we could leverage this feature. So there were a few tables that were not shardable, and vReplication also provided materialized view support, to support these tables. So we were very keen to use it, and we even POC'd it. But at the time, this API specifically was in the initial development stages, and it would require like a lot of monitoring and maintenance, and obviously had some stability issues. So we could unfortunately not leverage it at the time. The second thing that we considered was dual writes from the application itself. So that would have been a better approach compared to vReplication, which was unstable at the time. But it would again require a lot of changes within the application itself. And it could pose multiple challenges, right? Like things like, a two-phased commit or, higher latencies and things like that, right? So again, this is something that we also did not use. We felt, we needed a well-planned custom migration technique, and we could achieve it via statement-based replication, right? So here is how we tested and staging the custom migration technique with a few too many iterations. We let the informed API write to the traditional standalone MySQL node and change the MySQL archive logging logic in that node from row-based to statement-based replication. And that helps us, so statement-based replication basically helps us generate raw SQL statements that were first run on the primary and then on the replica, right? So this obviously also requires, statement-based replication obviously also requires us to have deterministic SQL statements. So we could not leverage things like, instead of a fixed timestamp, we could not use something like, now or some other construct which basically, fetch and construct these statements on the fly. We had to be deterministic about our queries. So once we had done all of that and made all of those changes, then we stopped one of the inactive replicas that we had. And we took a one-time database dump from that and applied it to the Vitess cluster. And then we use one of the Percona tools that allows us to replay bin log events from the last position in the dump. And thus we had a dual write setup on our side without making any application changes. So basically data goes into the primary MySQL. From there, it is replicated to a few of the replicas. And from one of the replicas, it is actually replicated to the Vitess cluster, all by leveraging statement-based replication and deterministic SQL statements. And for the staging setup, we used hash-based sharding, and Vitess provides custom shard names. So we had one range which was -80 and the other one which was 80 minus. Once there was no lag left, no replication lag left between the primary and the Vitess cluster, we validated the data across the traditional cluster and the basically the native MySQL and the Vitess cluster. And how we did that was comparing the primary of the standalone MySQL to the basically all the replicas that we had of the Vitess cluster to ensure that the data is consistent across the entire pipeline. And we also did this operation a couple of times to make sure that we have a solid migration plan in place. So a few observations that we had was that the count query latency in Vitess was much faster since the data is spread across multiple shards. And the same goes for primary key lookups. And since the data is spread across shards, the indexes are also shrunk, thus the improvement to the query performance. Even though native MySQL allows a direct access to the database, the latencies for Vitess were comparable. One big thing that we found was that we should avoid joins or cross-shard queries, as these can be super expensive. So we weeded them out, and we had a custom hook to manage such queries. We also found that the proxy services, VDTablet and VDGate, were quite memory intensive sometimes. So we need to tune the configurations to reduce the usage. And we also considered, having beefier boxes. So here is our final production cluster migration that was initiated. Few things to call out again is that we use hash-based sharding. So the names that you are seeing here are, things like AT to C0 represents a range of key space IDs that shard hosts. And each MySQL shard constitutes a replica in the same fabric and one replica which is in a different fabric or a data center. And we have multiple VTGate processes to scale writes. So we can leverage any of the VTGate process to actually do the write, and that gets synced up to the respective shard. And also to have high availability, we have also added HCD processes on every host in the cluster, so that the VTGate and the local VTtablet process has a local HCD to access the metadata instead of a remote host. Vitess does not support traditional auto increment feature and generates the primary key ID values sequentially for a given table. But it has a backdoor way, which is called sequences, that help mimic this feature. So sequence cluster is basically a non-sharded Vitess cluster that maintains a sequence table for each of the tables that we have in our traditional schema. And the VTGate reads the next ID from the respective sequence table and updates it by incrementing it once it has been used. We also set up MySQL Orchestrator, which is an out-of-the-box tool to provide high availability by initiating failover to a candidate primary in case the active primary fails. So currently, whenever a Vitess host goes down, the orchestrator has the understanding of the failover, and it updates the topology metadata to reflect the current primary host. For the sake of rollback, we also got creative and maintained a rollback cluster that basically reads data from all of the shards using multi-source replication. And that basically means that the final replica has 4 primary hosts from which it is reading the data and writing to one single MySQL database. And believe it or not, for production, we did the entire migration to Vitess and then going back to the native MySQL as a test run to make sure the plan is solid before we implemented the final state, which is again moving back to the Vitess cluster. So this ensured that we had a battle-tested rollback plan, which actually worked. And with all said and done, Inform today has 3 nines of availability. It ingests about 600,000 events a day, and this number just keeps going up. So these numbers are a little dated, so the actual figures might be quite high compared to this too. And all of the events that are consumed by Inform are made immediately searchable. So that basically allows all of our producers to read their writes. And the witness part,
just a heads up on the time check.
yeah. And so the witness part, MySQL backend serves 96.5% of all of the search queries that we have, and will well over like 500 million events and almost 6 billion rows. It does all of this with a 99 percentile latency of 100 milliseconds from the database to the application. So in conclusion, we saw how Vitess enabled Inform to scale to tens of billions of events without having to actually reinvent the wheel. In its current shape and form, the Vitess cluster actually serves 131 times the queries served by a primary search store, the Elasticsearch. We discussed how multiple online migrations with minimal downtime and billions of rows of data were performed with no user impact while ensuring data integrity. And also how it's crucial to have a backup plan that is actually battle tested, right? But with all of this said and done, we are still just getting started. Over the next year, we are on track to scale Inform to over 50x the scale that we have right now. And our investments into Vitess are going to be the foundation for it. So thank you. And if you guys have any questions.
Cool. Looks like I don't see any questions on the chat window as well. So we'll just wait for another 5-10 seconds.
So I have questions on pre-plan, like before, do you use statement-based replication before that? Like, did you modify your MySQL to support statement-based replication to make this Vitess migration? Okay.
Yep. So as you know, statement-based, once you enable statement-based replication, you need like basically whatever queries that you fire need to be deterministic. You cannot fire an indeterministic query like insert into whatever table where something like, let's say timestamp value equal to now, because once that is replayed on the replica and is an indeterministic SQL statement, the value in the primary versus the replica would be different. So we had to look at all of these indeterministic SQL statements that we had in like across our code base, and we had to modify each of them to ensure that we only have deterministic SQL statements that can be replayed safely or across the replica and then the Vitess cluster.
Thank you. So one more thing, what is the Percona tool used for binlog replay?
I do not recall the exact name of the Percona tool, but I can actually once I can look it up and I can post it in the Slack channel if that would be helpful.
Okay, thank you.
Vitess for PostgreSQL,
yeah.
I actually do not have much idea about that. I'm sorry. Yeah, Prem, you were saying something.
No, yeah, you noticed the question on the chat window. I was about to reread it. Cool. Looks like we are done with the Q&A as well. Hey, thanks a lot, Dipanshu, for the detailed walkthrough about the Vitess. In fact, like it was super verbose, fascinating every phase of the development, along with the architecture and schema design. And interestingly, the challenges faced during the online migration and schema migration was quite useful, and really quite excited about the future as well. Thanks a lot, Dipanshu. With this, like I hand this over to Dipanshu.
Thanks, Prem. Thanks, Batri, and thanks, Appu, and all the LinkedIn folks for extending their hosting facility for the event. Thanks, all the speakers. Without the speakers, this community is actually dead. So we need more of volunteers like you. Please spread the word to your friends that we share our learnings to enrich the community. So to the tune of today's talks, the spirits were like perfect to the open source open source world. Everybody shared to the extent which is possible, almost like all architecture diagrams even. So this is great spirit. And I would like more such in the coming days. Our next event would be in January to end our 10th year journey. And would like to request everyone to join. So if everyone can open up their videos for a moment, what we can do is we can take few screenshot of the participants in the same gallery view. So request everyone to come on the video and open their videos for a moment. I could see Shanmuga, Sarguru not on video yet. Please come. Asif, Rahul, Tanya, Deepak. Yeah, I could see few more. Girish, Bala. If you come on the video, then I can take a screenshot. Bala is still mute and not on video. Okay, so I'll go ahead and think Ashutosh joined later. Girish also joined later. Thanks, guys, for joining. Asif, if you are listening, please open your camera for a moment. Okay. 3, 2, 1. Thank you. Thanks, everyone. Have a nice weekend. It was a great learning with all of you. And let's meet in January. Thank you very much.
Thanks, everyone.
Thanks, everyone.
Thank you.